last two lessons, we've been talking about the dot product. The dot product applies only to n space. In other words, it would be vector spaces that are subspaces of Rn. In today's lesson, we're going to generalize the concept of dot product and call it the inner product, and the inner product will be defined on any vector space. So we're going to move from n space to any vector space. We're going to talk about the inner product. To help you keep it straight, you can think of the dot product is to n space as the inner product is to any vector space. Now I'll give you some notes on what I've just told you. The dot product is a special case of a more general concept, that of inner product. The dot product is an inner product defined on Rn. Now actually, we define an inner product as being any operation that will satisfy the properties that we talked about before of a dot product. So definition: let U, V, and W be vectors in any vector space V, and C be a scalar. An inner product, and notice I said an inner product rather than the inner product. There may be more than one. An inner product on V is a function that associates a real number, and this is the notation for inner product, a real number, UV, with each pair of vectors, U and V. So we have a pair of vectors, we perform the inner product, and that will give us a real number, a scalar. And this is the notation we use for inner product. That satisfies the following axiom. So this function has to satisfy the following axioms. And you'll recognize these axioms as being those that we use for dot product. UV is the same as VU. In other words, the inner product must be commutative. The inner product must be distributive over the vector addition. U, V plus W, is the same as UV plus UW. So the inner product must be distributive over the vector addition. The scalar outside the inner product can really be put with the U or the V. In this case, we only put it with the U. The inner product of V with itself must be greater than or equal to 0, and it can be equal to 0 only when V is 0. So any function that associates a real number with each vectors U and V satisfying these four conditions will be called an inner product. Let's look at an example. Let's let f and g be real valued functions in the vector space C, -1 to 1. In other words, it's a set of all, the vector space would be the set of all functions continuous over the closed interval from -1 to 1. And let's show that the inner product fg, defined to be the definite integral from -1 to 1 of f of x gx dx, is an inner product. We'll show that the inner product with this definition is actually an inner product. In other words, that it does indeed satisfy the four properties. Well, to show that it satisfies the four properties, we just have to show that it's commutative, distributive, you can multiply in the constant, and that the inner product of a function with itself is positive or zero. So we'll look at the commutative property first. Okay, we'll start with fg. Well, fg is going to be the integral from -1 to 1 of f of x g of x dx. Well, I can write this as the integral from -1 to 1 of g as a function of x, f as a function of x dx, which is gf. So condition 1 is satisfied. Now for condition 2, let's consider f with g plus h. Well, that would equal an integral from -1 to 1 of f of x g plus h as a function of x dx, which is equal to the integral from -1 to 1 of f as a function of x times g as a function of x plus h as a function of x dx, which is equal to integral from -1 to 1 of f as a function of x times g as a function of x plus f as a function of x times h as a function of x dx. Well, since the integral sum is the sum of the integrals, I can write this as the integral from -1 to 1 of f of x g as a function of x dx plus the integral from -1 to 1 of f as a function of x h as a function of x dx. Which is equal to the inner product fg plus fh. So we have proved that the definition is distributive over vector addition. Now for the third property, we want to start with C, F, G. Well, this would equal to C times the integral from -1 to 1 of f of x, g of x, dx, which is the integral from -1 to 1 of C times f of x times g of x dx, which is equal to integral from -1 of f of c of x, g of x dx, which actually I didn't need this because this is really what I want. This would be CFG, which is what I was trying to prove. Okay, the fourth one, we want to show that the inner product with the function itself is always positive or 0. So we'll look at f, which would equal to the integral from -1 to 1 of f of x dx, which is equal to integral from -1 to 1 of f of x quantity squared dx. Now since this is an even function, this would equal an integral from 2 times integral from 0 to 1 of f as a function of x f of x function of x quantity squared dx. Well, this is greater than or equal to 0, because this would obviously be positive. I'm integrating over 0 to 1, so we're going to have a positive integral. Furthermore, by looking, I can tell the only way this quantity could be 0 would be for f of x to be 0. Remember, area is interpreted as the area under the curve. So f of x quantity squared is going to be positive, so it's going to be up here. Or it's going to be on the line. Well, if it's up here, then obviously we have a positive area. If it's on the line, the answer is 0. And the only way it can be 0 is to be on the line. So therefore we've proved that it is an inner product. So the definite integral from -1 to 1 f of x dx defined over the set of continuous functions, continuous on interval -1 to 1, is an inner product. Let's show that uv, which is equal to u1v1 minus u2v2, where u and v and r2 is not an inner product. Well, all we have to do is to find one of the properties that fails to be true. So let's go for property 4. Let's let u be the vector -1, 3, and let's show that u greater than or equal to 0 fails. So show that u greater than or equal to 0 fails. Well, we would have -1, 3, -1, 3 would equal to, using the definition now, it's u1v1 minus u2v2. So it would be a -1 times -1 is 1, minus 3 times 3 is 9, which is equal to a -8, which is not greater than or equal to 0. So therefore, is not an inner product. All the things that we developed with dot product follows for inner product. And so I'll just call them extensions. Let U and V be vectors in an inner product space V. The norm, the norm or length of vector U is denoted the same way. The norm of U is equal to the square root of the inner product, U with U. The distance between U and V is just the norm of U minus V. The angle between two non-zero vectors is given by cosine theta is equal to the inner product of UV divided by the norm of U times the norm of V. U and V are orthogonal if and only if the inner product of U and V is equal to 0. The magnitude of the inner product is less than or equal to the norm of U times the norm of V. So if I take the inner product and then take the absolute value, I will get an answer that's less than or equal to the norm of U times the norm of V. If U and V are vectors in an inner product space V, then we don't need these. U plus V, the norm of U plus V is less than or equal to the norm of U plus the norm of V. So U and V are defined to be in an inner product space. They're in the inner product space, but obviously it didn't make sense to have the inner product symbols with U and V there, U plus V. And the Pythagorean equation holds true. U and V are orthogonal if and only if the magnitude of U plus V quantity squared is the magnitude of U squared plus the magnitude of V squared, or the norm I should be using with inner product. Let's look at an example. Let's let A and B be vectors from M to 2. In other words, a set of all 2 by 2 square matrices. We'll define the inner product for between A and B to be 2 times A11 times B11 plus A12 times B12 plus A21 times B21 plus 2 times A22 B22. Whereas I'm multiplying the components A11, B11, and then multiplying that by 2. The inner ones I'm just multiplying together. 3 times -2, 4 times 1, and then the last one I'm again multiplying them and then multiplying by 2. Well, let's find AB. Well, using the definition, AB is going to be 2 times negative 1 times 0 2 times A11 B11 plus A12 B12, so it'd be 3 times negative 2 plus A21 B21, that's going to be 4 times 1 plus 2 times A22 B22. This is A22 B22. Well, this is of course 0 plus negative 6 plus 4 minus 4, which is negative 6. So the inner product of A and B is negative 6. Let's evaluate the norm of A. Well, we know the norm of A is going to be the square root of the inner product of A with A. And I'll write A down here for reference. Negative 1, 3, 4, negative 2. So this would be the square root of, now to do the inner product, it's going to be 2 times negative 1 times negative 1 plus 3 times 3 plus 4 times 4 plus 2 times negative 2 times negative 2. That's using the inner product that we defined in the previous example, and I'm using the same ones. So it was 2 times A11 B11 plus A12 B12 plus A21 B21 plus 2 times A22 B22. This is going to be the square root of 2 plus 9 plus 16 plus 2 times 2 is 4. 4 times 2 is 8, and it will be positive because the negative times negative is positive. This is going to be the square root of 25 plus 10 is 35. Because 9 plus 16 is 25 plus 10 is 35, that's right. Find the angle between A and B. Well, we know that cosine theta is the inner product with A and B divided by the norm of A times the norm of B. Now we've already calculated the inner product of A and B. We got that to be negative 6. We've already calculated the norm of A. We got that to be the square root of 35. So we need to calculate the norm of B. Well, we can see what B is. So the norm of b is going to be the square root of the inner product of b with itself, which is going to be the square root of 2 times 0 times 0 plus a negative 2 times negative 2 plus 1 times 1 plus 2 times 1 times 1. Well, this is going to be 0, so it's going to be the square root of 4 plus 1 plus 2, which is the square root of 7. So the norm of b is the square root of 7. Using the calculator, I get this would be negative 0.3833259. So we have cosine theta is equal to this number. Well, theta reference, or the cosine of theta reference, would be the positive 0.3833259. So put my calculator in degree mode and hit inverse cosine, and we get that theta reference is 67.46 degrees. But now, since cosine is negative, that means it's in the second or third quadrant. Well, we're defining the angle to be between 0 and 180, so it's going to put it in the second quadrant. So theta is equal to 180 degrees minus 67.46 degrees, or theta is going to be 112.54 degrees.